Human working memory is a severe processing bottleneck. During knowledge acquisition, it requires precise architectural management to prevent cognitive overload. For a novice, worked examples provide that management. By supplying a fully solved problem step by step, they minimize the need for trial and error, reducing the randomness as genesis principle. However, this reliable instructional tool contains a limitation known as the expertise reversal effect. As a learner successfully builds schemas in their long-term memory, the same instructional scaffolds that were once helpful begin to actively decrease their problem-solving performance. This transition suggests that instructional scaffolding is not a constant. It is a dynamic variable that should decrease as schema acquisition increases. This diagram illustrates the constraints of working memory when interacting with novel instructional data. Total capacity is divided between intrinsic load from the task, extraneous load from the instructional design, and remaining freed capacity. In a novice state, high problem-solving demands consume all processing resources, leaving little capacity for schema construction. Robust long-term memory schemas bypass these limits. The brain organizes multiple interacting elements into a single unit, which shrinks the extraneous load and frees working memory for more complex processing. If a system forces an expert to process step-by-step external guidance that duplicates their internal schema, it triggers a redundancy penalty. The extraneous load increases because the brain must use energy to integrate unnecessary external information with existing knowledge. Redundant external guidance conflicts with the narrow limits of change principle. To maintain cognitive efficiency, expert instruction must remove support to minimize this extraneous load. The completion task serves as the structural bridge between a fully worked example and unguided problem solving. Instead of an abrupt transition, an instructional system can use fading, the progressive replacement of instructional steps with independent problem-solving demands. This diagram shows an algebraic procedure testing fading mechanics. In backward fading, the system provides initial steps while the learner supplies the final step. Forward fading omits the very first step, the critical setup, while providing the subsequent path. While both methods facilitate learning, backward fading typically imposes a lower initial cognitive load. Because the learner supplies only the final step, it often leads to better results in both near and far skill transfer. By dissolving guidance step by step, the system preserves sufficient working memory capacity for active schema construction without triggering cognitive overload. Expertise does not develop at a uniform rate across all learners. Research by Martin Reislein shows that rigid fading schedules result in significant learning delays that depend on a student's prior knowledge. Advanced learners subjected to slow fading experience a redundancy penalty. They already possess the necessary schemas, yet the system requires them to process redundant steps. Conversely, fast fading can cause cognitive overload in a novice. Without foundational schemas, they are required to solve problems independently before they have the resources to do so. In highly complex, poorly structured domains, these imbalances in cognitive load can lead to significant performance errors. In high-stakes environments like air traffic control, fixed instructional schedules can be a liability. Task difficulty must map directly to a learner's real-time capability. The engineering challenge for these systems is measurement. To optimize learning, a system must assess a learner's exact expertise level in real time to determine the correct fading phase. To solve the timing problem, instructional designers applied foundational research from cognitive psychology. In 1965, Adrian de Groot studied how master chess players recognize patterns on the board. De Groot assessed players by measuring their responses to briefly presented board states, often using time limits to distinguish masters from novices. He demonstrated that experts do not perform slow, sequential analysis of individual pieces. Instead, they retrieve high-level schemas from long-term memory to instantly recognize problem states and appropriate moves. Novices lack these organized schemas. They are forced to analyze random, lower-level components of the board one by one, which taxes their working memory. This suggests that the nature of a subject's first move reveals the structural depth of their underlying long-term memory schemas. Modern intelligent tutoring systems adapt de Groot's findings into an algorithmic diagnostic tool. This first-step diagnostic measures long-term memory in real time. A novice might guess their first step through trial and error. An intermediate executes a standard procedural step, dividing both sides by 4. An expert instantly bypasses intermediate steps, producing the final answer immediately. In less structured domains, A rapid verification method where learners quickly identify a step as right or wrong provides similar diagnostic validity. These microassessments provide instantaneous data, allowing the system to route learners to the appropriate fading stage without traditional time-consuming tests. This real-time measurement enables expertise-based adaptive fading. This architecture uses rapid diagnostic probes to govern the entire learning process. Failing the initial first-step diagnostic routes a novice to stage 1, where fully worked examples help build foundational schemas. A learner who passes the diagnostic moves directly to stage 2, beginning with completion tasks that demand more independent problem-solving. Instruction remains tailored through a phase-exit diagnostic loop. If a learner fails to demonstrate schema acquisition during practice, the system loops them back to more explicit examples. As expertise solidifies, the system reaches the terminal stage. It removes all explanations and leaves only pure, unguided problem-solving. This architecture manages the expertise reversal effect by maintaining an equilibrium between working memory load and the learner's available capacity. Static instructional scaffolds in high-complexity domains can lead to redundancy for experts, while leaving novices without the support they need. Cognitive efficiency is improved when external support matches internal memory structures, withdrawing guidance precisely as a learner gains expertise. Precise instructional design depends on engineering architectures that identify the exact moment to fade guidance to zero.